Hi everyone, welcome back to the Microsoft in 29 days and welcome back to Geeks for Geeks practice. In case if you have still not registered for the Microsoft in 29 days course, so make sure to register for this free self-paced course. You can find the link of this course in the description of this video. It is absolutely free of cost. Once you register for this course and click on the start button, then you will be able to access all the 29 days that are there in the series. Like let's say if I click on day 16, then you will find that you will get two recordings of the problems, two medium level problems, medium or hard level problems that I do as classwork. So you'll find the recordings of that. You can also find these recordings on YouTube. Apart from this, you will also get to solve 5 problems, 3 problems that I give as homework and the other 2 problems that we solve as classwork. So make sure to register for it, because not only this, you'll also get access to the leaderboard. You can also find yourself on the leaderboard to track that what is your progress amongst other people. So make sure to register for it. Let us discuss this problem, that is union find. So the problem says that this problem is to implement disjoint set union, and there will be two incomplete functions, namely union find and find. And what you have to do is you have to complete these two functions. So union is the joining two sets, and is connected will check whether the two elements belong to the same set or not. Okay, same subset or not. So what you have to do is, first of all, we need to know that what is this data structure, that is also known as disjoint set union. Okay, so in this what happens, suppose I tell you that okay, 1 is there, okay, 2 is there. Suppose I have 5 elements, 1 is there, 2 is there, 3 is there, 4 is there, and 5 is there. So let's say, like we initially said that 1 is connected to itself, 2 is connected, like initially all of them are separate components, right? They are belonging to themselves, right? They do not belong to any other set. So we will say that we will have a parent array representation for that. Okay, for this we say that we have a parent array representation like this, like 1, 2, 3, 4 and 5. And for 1 in the parent array we have 1 stored only, for 2 we have 2, for 3 we have 3, for 4 we have 4, for 5 we have 5, because initially they will belong to the same parent. Okay, now here we can use a find function and we can use a union function to do the union and finding the ultimate parent. Let's say if these people, if all these 3 elements belong to the same group, okay, if they belong to the same group, then we used to do what, let's say we talk about classes in terms of class, or in our college or maybe in our school, we used to have class representatives, that is nothing but the CR. So CR used to represent that, okay, what is the, like CR used to raise our issues to the concerned authorities and things like that. So basically CR used to represent a group of people, right, their opinion. So similarly, if I want to know that whether all these belong to the same component or not, so basically I'll make their parent as 1. Okay, that is what I will do. So basically what I will do is, let's first of all check. So let's say initially they are their parent, their own parent. Okay, now what I want to do is, I want to do the I want to do the union. Let's say I do, like I will first of all check. So let's say I want to do the union of 1 and 2. So can I do that? Yes, I can do the union of 1 and 2. Why I can do that? Because they belong to, their parents are different, right? Parent of 1 is 1, parent of 2 is 2. So maybe what I can do is, here initially we can think of, like we'll talk about the optimizations later, but let's say I mark that okay, 2's parent is 1. So I'll update this inside the array as well, and I'll mark the parent of 2 as 1. Okay, after that, let's say I do the union of 1 and 3, or let's say 2 and 3. Okay, so you know that if A is a friend, like you know that if A is a friend of B and A is a friend of C, then B and C also become friends, or B and C also become part of the same group, correct? So similarly, what we will be doing here is, if I do the union of 1 and 3, then what, like if I do the union of 2 and 3, okay, suppose that I do the union of 2 and 3. So if A is a friend of B and B is a friend of C, so that means A and C are also connected. Okay, so what I will do here is, I'll simply say that now, like 3 will be pointing to 2, okay, because 3's parent will become 2, so I'll mark it like this. Okay, this is how it will happen. Now there's one thing that more that we need to understand. Suppose this is how we are doing the union, right, one by one. But if I have to find, like, let's suppose we do this. Okay, so suppose what we do is one by one. Suppose these are the nodes that we had. Okay, suppose this was 1 2 3 4 5, and these were the parent child relationship looked something like this. And I will, like, suppose there's an element, like suppose there's 7 8 like this. Okay, if I have to do the union of 8 and 5, so will I do the union? Yes, I will do the union, because the parent of 5 is what? The ultimate parent of 5 is 1, right? So the group representative of 5 is 1. The 5 belongs to the group in which the leader is 1, and 8 belongs to the group in which the leader is 7. So that means I need to do the union of the two groups. But before that, like, if I am again and again trying to find that, okay, what is the parent of 5? Okay, so I will take a lot of time, because if I have to find the parent, so that actually takes a lot of time, because I have to, like, first of all I'll be at 5. Okay, so I can write a recursive function, let's say a find function. Okay, in which first of all I will have access to the node v, and I'll have access to the parent array as well. Okay, so see, if, what we can say, if the parent of v was equal to v itself, right, in that case we can return, right, because if one parent is 1, then, like, if it is not, then we will keep on moving up, right, we'll keep on moving up, right? But if the parent of v, if suppose that we talk about 5, so for 5 the parent is 4, which is not a parent of itself, so we'll call for 4. Then the parent of 4 is 3, which is not pointing to itself, then we'll call up. So parent of 2 is what? 2. Parent of 2 is 1, so we'll call for 1. Now parent of 1 is what? 1 itself. This basically indicates what? This basically tells us that in this case we can say that this is the ultimate parent. So whenever the parent of v is equal to v, in that case we can say that we'll return v only. Else what we will do is, else otherwise what we need to consider is, we need to consider that we will return what? We will return finding the parent of v comma v. Now why will we do this comma the parent? Why? Because let's say we find that, okay, the parent, like, if we did not find, right, so if for 5 its parent was not itself, right, so in that case what did we do? We called for this guy, right, we called for the parent of 4, like we tried to find what is the parent of 4, correct? So if we were at 5 and 5 parent was 4, so now we'll try to find the parent of 4, correct? So that is why we are finding the parent of current node v, right? So we'll call for it, we'll call up, then we call up again, then we call up again, then we get what? We get 5 for this guy. Like we get 1 here, like we get 1 in return here also. This also returns a 1, and this also returns a 1. Then 5 gets to know that, okay, the ultimate parent is 1, but actually this takes a lot of time. And if I only want to find the ultimate parent, so for this, if the chain is very large, so it will take order of n time for finding, which is very very high. So what I can do instead is, while I'm returning, so I can say one more thing, that while I'm returning, so in the else part, what I can say is, I can say that if I'm returning and I want that okay, parent of 5 is 1, ultimate parent is of 5 is 1 itself, right? So what I can do is, I can do the path compression technique. And what I can do is, I can simply say that 5 will point to 1 only. Why? How? Because if I was at 2, so 2 was pointing to 1, but when 2 gets 1 in return, so it will start pointing to 1 again. So basically this connection will not change. But 3 was pointing to 2, but when 3 gets 1 in return, right, 3 gets 1 in return from the function, right? So what we'll do is, we'll mark the parent of 3 as 1 itself, right? So we'll say that parent of v is equal to find the parent of v comma parent array, right? This is what we'll do. So basically we'll update the parent while returning also, so that what will happen, you can see now what will happen for 4 also. We'll do the same thing. So now 4 will start pointing to 1. Okay, after this what will happen for 5 also, like when it gets 1 in return, so 5 will start pointing to 1 again. Now you can see that what is happening, the size of the length, like the length that we had, order of n, now it reduces, right, it reduces to order of 1. So now if someone will ask me that, okay, what is the parent of 1, or what is the parent of 5, what is the group to which 5 belongs, so I can directly find the parent in very very fast time, that is order of 1 time most of the times, correct? Because if someone will ask, so now 5 is connected to 1, so that's how I'll return. So this technique is known as path compression, right? This technique is known as path compression in union find. So let's try and write the find function here. First of all, and see what we will be doing here. So what we will be doing here is, like, first of all, here we have not been given a find function, so we'll write in find function. Okay, in this we'll have the node v, and we'll have the parent as well passed. Okay, so what we will be doing here is, we'll say that if the parent of v is equal to v, then we will return simply nothing but v. Else what we will do is, we will return, like earlier what we were returning, we were returning find parent of v, right? We are returning earlier find parent of v comma the parent. But now what we will do is, we'll also, like, if we want to do the path compression, right? If you also want to do the path compression, if you also want to do the path compression, in that case what we will do is, we'll say that, okay, parent of v is equal to this thing, right? Parent of v, like, we'll update when we return, we'll also update the parent of v, right? So that the cycle, like the cycle is not very large actually, like it, this is how it will look like ultimately. Okay, because I can, in order of one time I can find, so this is nothing but the path compression process. Now also one more thing that they are asking is, they are asking to implement a function in which we have to find whether it is like whether a and b belong to the same group or not, whether they are connected or not, whether they belong to the same subset or not. Correct. So if they give me, let's say we have some arrangements like this, let's say we have some arrangement like this. All right, so if we have an arrangement like this, and other thing that we have here is, suppose we have, okay, we have this kind of an arrangement. So if I'll ask you that, okay, r5 and like r, like, suppose that after, like, if I ask you that, okay, are 4 and 8, 4 and 7 connected, or are 4 and 7 belonging to the same subset, you will say no. Why? Because they belong to different subset. Because when you will do the union find operation, then not only you will change the connections one by one like this, okay, the connections will get updated like this, but actually the parent of 4 will be 1. Okay, parent of 4 will be 1, correct? And for 5, when you will do the same operation, so this will point like this. Okay, so for 7 the parent is 5. So now you can see that they are belonging to different groups. In that case, if the ultimate parent is different, after finding, after using the find operation, right? So for a, you do what? You do find the a, find parent of a comma the parent array you will pass. Okay, for b also, if you are finding the ultimate parent, so you'll call in this recursive function. Okay, and you'll pass the parent. So if a is equal to b, right, in that case you will do what? You will return true, because they will belong to the same component. If I ask you that, okay, 4 and 5 are belonging to the same subset or not, so you will say that yes, 4 and 5 are belonging to the same subset. Why? Because you can observe 4 and 5 are belonging to the same, like 4 and 2 are belonging to the same subset here, because their ultimate parent is the same. So in that case, if a and b's ultimate parent is the same, then you will return a true. Else what you will return is, you will return a false. So let's try and implement the connect function as well here and see. So is connect function is given to us. Okay, so we will do what? We will say that x is equal to find x comma parent. Okay, and then y is equal to find y comma the parent array also I'll pass. Okay, after this part is done, so I will say that if x is equal to y. Okay, so then we will say that, okay, they are connected, because if they have the same parent, if they have the same representative, then they are connected. So I'll return a true, otherwise I'll return what? I'll return a false from it. Okay, now I need to implement the union function as well. So when I implement the union function, right, if suppose this is structure I have, right, if suppose that the structure that I have had was something like this. So if I have to implement the union function, that is, if suppose that if this was the structure that I had. Okay, if I had like this, something like this, so what we now need to do is, now need to understand that whether they are belonging to the same part or not. Okay, so if I ask you that, okay, if I have to do the union of 5 and 7, so will you do it? Will you do it? Yes, you will do it. But if I ask you to do the union of 4 and 3, will you do the union of 4 and 3? No, because they belong to the same parent, right? Because they are connected. So what we can write in the union function is that if like, first of all, we can say that if is connected function is there already implemented. So if is connected, let's say x comma let's say a comma b comma the parent array comma the rank 1 array, right? If this function returns me a true, if it's is connected for a, b returns me a true, in that case what I will do is I'll simply return from here. Why will I return from here? Because if they are already connected, if they have the same parent, then they will be connected and I do not need to connect them, right? because they will be belonging to the same subset. Otherwise, if they are belonging to different subsets, let's say if I have to do the union of 4 and 7, so since they will be belonging to different subsets, so in that case what will I do? I'll simply say, like, if suppose that 5 and 7 were there, so if I have to do the union, right, so in this case you can say that either I can make the parent of 1 as 5, okay, or I can make the parent of 5 as 1, but both of these things are different, right? If I have to do the union of 4 and 7, then both of these things will have different meanings. Why? Because what will happen here is, suppose I have 5 here, right? Suppose what I do is I make 1 as the child of 5, okay, so if I make 5 as the parent of 1, like this, okay, then you will observe something with this chain, something is happening with this chain, and what is happening, you can see that. So if you will observe now, so earlier what was the size, right? This is the ultimate parent, right? Earlier the height, this much height, the height of this component was 4, and the height of this component was 2. Now if you will observe, so the height of this component becomes 5, it increases, right? So if you merge the larger like in the larger guy, the larger component to the smaller component, in that case what will happen? What will happen is the length increases, so the number of traversals required will increase, okay. But what will happen when you merge 5 to 1? Okay, if you merge 5 to 1, then what will happen? So let's see that as well quickly. So in this case, if I'll see this part, if I'll have 1, then 2, then 3, then 4, okay, 1 is connected to itself, then let's say 5 starts pointing to 7, and here, now if you will see, so height still remains the same, correct? That is the part. And if they both had the same height, then you can mix anybody with anybody and update the parent as well as the size. So this technique is known as nothing but union by rank, or you can basically say union by size, okay. And this overall, this makes the operations amortized. Basically it says that in order of one time, usually you are in constant time, you are able to do the job in union find data structure, right? Because if you had been using graphs, so this would have taken a lot of times in terms of adjacency list, deleting the connections and all would have taken order of n time, okay. So what I will do is, if they are not connected, right, else if they are not connected, so what I will do is, first of all I'll find the parent. So I'll say that a is equal to find a comma parent array I'll pass, okay, and b is equal to find b comma parent, okay, array. Now I will check that if the rank 1 array denotes the size, so if the rank 1 of a is greater than the rank 1 of b, okay, so in this case what will I do? If the rank 1 of a is greater than the rank 1 of b, so that means a is of greater size, so if I will merge the smaller into the greater, right? So I'll say that parent of b is equal to a, okay. Else if it happens that the rank 1 of b, right, if the rank of b is greater than the rank of a, in that case we'll say that parent of a is equal to b, right, because we'll merge the smaller into the larger. Otherwise, if they both have the same length, then we will do what? We can maybe say that parent of b is equal to a, okay. So a will get like a will become the parent of b. In that case we need to increase the rank of a here, okay. So that is what we will be doing in the union function. Let's try and compile this code. It works on the samples. Let us try and submit our code as well. So you can see that our solution was able to pass all the test cases in constant time for each and every query. So in case if you understood this explanation, so make sure to hit the like button and comment on understood as well. Thank you. In this video, we will discuss the problem detect cycle using DSU. So the problem says that we will be given an undirected graph with V nodes and E edges. So our task is to check if the graph that is undirected graph that is given to us, if it has a cycle or not. And we don't have to do it using normal recursion or normal DFS traversal. You have to solve this problem using disjoint set union, as we have discussed in the previous video. So what we have to do here is, suppose that if we have been given a graph like this, like 3, and then let's say we have 4 also. So if I consider this graph, so does it have a cycle? No, it does not have. But let's say 4 was also connected to 1. In this case, it does have a cycle. So for that, we need to return that, okay, when this graph combination is given to us, in form of adjacency list, then we need to return a true. Otherwise, if no cycle is present in the graph, then we need to return a false. So how can we do this particular problem? So either we could have done what? The first way of doing it would have been, we would have used the DFS approach, right? We would have used the DFS approach and checked that using the visited array, that if a particular child is already visited and it is not the parent, then we can say that the cycle exists in the graph. But here we have to apply the disjoint set union for solving this particular problem. So what we can say here is, let's say we are given the edges like this, okay? So basically we will be given, let's say we have been given the graph like this. 1 is connected to 2, let's say, okay? Then 1 is connected to 3 and 2 is connected to 3. So this means in the adjacency list of 1, 2 and 3 will be given. In the adjacency list of 2, 1 and 3 will be given. In the adjacency list of 3, 1 and 2 will be given, okay? So what we'll be doing here is, we will simply traverse the adjacency list of each and every vertex. Like when they say that okay 1 and 2 are connected to each other, then what we will do is, let's say that one, like when they say that okay 1 and 2 are connected to each other, right? Because in the adjacency list of 1, first we are traversing. So in the adjacency list of 1, 2 is present, okay? So if in the adjacency list of 1, 2 is present, so initially all of them will be their own parent, correct? So initially they all will be their own parent. Like if we talk about the parent array here, so it would look something like this. Like everybody will be pointing to itself, like 1 2 3, and here we'll have 1 2 3. Okay, now what will happen when I see that 1 and 2? So if I check for 1 and 2, so are 1 and 2 connected to each other? The answer to that will be false, and if it is false, then I can directly connect 1 and 2. So since both of them are having the same rank, so I will also have a rank array which will be starting from 1, because I'll also keep a track of the size of the components. So I'll connect 1 with 2. Let's say I make 1 as the parent of 2. After this, when I see 1 and 3 inside the graph, so what I will eventually do is, let's say if I see 1 and 3. So in this case, when I see 1 and 3, so we can observe here that 1 is not connected to 3 currently. So they belong to different components, but now they should be connected. So after this, what I will do is, I'll connect 1 and 3 both, right? So that means that the parent of 3 is also 1. Okay, so parent of 2 gets updated to 1 and parent of 3 also gets updated to 1, right? Now this does not mean that we have a cycle, because if you see, so from 1 we are having an edge to 2, correct? Then from 2 we are having an edge to this guy, that is 3, like no, from 1 we are having an edge to 2, and from 1 we are having an edge to 3, correct? So this is the current graph that has been made here, right, up till now, up till this point of time. Now if you will observe, so like one more thing that I want to make you understand before starting. So let's say if one was one was like in the adjacency list of 1, 2 was present, suppose, and in the adjacency list of 2, 1 was present, suppose that only this edge was there. Suppose they said that okay 1 is connected to 2. So now if 1 is connected to 2, initially what will happen, basically initially what will happen here is, both of them will be pointing to themselves only, correct? So in the array, 1 will be pointing to itself, 2 will be pointing to itself. Now when I traverse the adjacency list of 1, so I see that 1 is not connected to 2, so I'll connect it. So basically I'll mark 2 connected with 1. When I mark 2 connected with 1, in that case what happens, the parent of 2 is now 1, okay? So you will observe that there is one problem here, because I will be traversing the adjacency list of 2 as well, okay? So when I traverse the adjacency list of 2, okay, so suppose that these values are I, right? These are I values. This is one vertex I, this is another vertex I, right? One by one, if I keep on moving. So suppose that these are the nodes present in the adjacency list, right? So I will say, now will you check? Now if you check, so according to the logic, like you can see what is there. It says that 1 is connected to 2. That is only there, right? Nothing else is there. But if you will check now, is like if you check, so in the adjacency list of 2, 1 is present. So now when you check, so it will give you what? It will tell you that okay, the parent of both the elements is the same, right? They both belong to the same component. They both belong to the same subset. But should you return a cycle? Because if they belong to the same subset and still you are wanting to join them, so should you join them? No. So basically in this case there is no cycle existing. So you need to, like, you will not return a true because both of them have the same parent. Because what you need to consider is if you have already made the pair 1, like if you have already connected 1 with 2, right? So then you will not want to check 2 with 1, right? You will not want to check this pair, because if you check 2 1, right? So that will give you a cycle, because one having the parent as 1, 2 is having the parent as 1. So this will be the cyclic condition, but actually there is no cycle existing. So you will say that you will check it until I is lesser than j only, right? Because you will check for the pair 1 and 2 only, and if it is not connected, you will make the pair. And once you make the pair, you will not check for 2 comma 1, because 2 comma 1 will start give you a cycle, whereas actually there is no cycle existing, right? So this is one thing that we needed to keep in mind. So I is lesser than j, that is one thing that we need to keep in mind, that is the for the current node, the element in its adjacency list should be greater than it. Okay, that is what I have observed. Now in this case, if I'll see, so since, like, will we check for the pair 2 and 1 now? No, we will not check it. Okay, so now since the element in the adjacency list now is greater, so 2 is greater than 3, so I'll check for the pair 2 and 3. So are 2 and 3 connected to each other? Like if I see here, so 2 and 3 are not connected to each other, but am I right? No, because if you will see, so actually 2 and 3 are connected to each other. Na? You will see here, like like 2 and 3 are directly not connected to each other. But if you will see in the graph, so both have the same parent. So that means that they belong to the same component. And if I merge them up, right? If I draw a edge between 2 and 3, so that will make a cycle. So this indicates, now because you can see, like when I find the parent for 1, so it is 1. When I find the parent for like when I find the parent for 2, and when I find the parent for 3, so both of their parent is 1 only. So that means they belong to the same component. And if they belong to the same component, so if I draw an edge between 2 and 3, so this will give me a cycle. So in that case, I need to return 1 or true, indicating that yes, there is cycle existing, otherwise there is no cycle existing, right? So this is one thing that I needed to keep in mind while solving this particular problem. So let's try and quickly write the code for this approach and see what will happen here. So as I discussed, we'll be having the parent array, we'll be having the rank array and everything. So first of all, let us quickly write the find function as well. So let's say we write the find function. In the find function, as I mentioned, we will be using the path compression technique. So I'll pass the parent, right? I'll pass x, I'll pass the parent, and I'll check that if x is equal to the parent of x, right? If the parent is the same, then in that case we can simply return lx. Otherwise, what we will do is we'll do path compression. So we'll say that parent of x is equal to nothing but find parent of x comma the parent array, right? So basically I've written the find function here. After this, I also need to write the union function, but before that, let's write the main function a little bit. So we will say that okay, we need a parent for the v nodes, all the v nodes, and we need the rank array as well for the v nodes, right? Because we'll be applying the union by rank and the path compression, both the techniques for optimizing our DSU, right? After this part, what I will do is I'll simply iterate, and I'll say that for int I can start from 0, I is lesser than the v, and then I plus plus. And after this, what we will be doing is, like, I'll simply mark all the parent, like I'll simply say that the parent of I initially is I, because it is connected to itself only, and I'll mark the rank of each person, each of the ith person, as 1, because there's only one guy that is itself, it is connected to itself, right? After this part is done, so what I will be doing is I'll be running a for loop for all the vertices. So I starts from 0, I is lesser than the v, and then I plus plus. After this part is done, so what we'll do is we'll say that okay, I need to iterate through the adjacency list to int j is to adjacency of I. So I'll iterate, j will help me to iterate through the adjacency list of the current node I. And what I need to check is I need to check if I is lesser than j first of all. And if I is lesser than j, and let's say I write a union function that returns me union function will not only do the union for me, but it will do the union when the two nodes are not connected to each other, then it will do the union. And if they are already connected to each other, then in that case it will return me a true. Okay, otherwise if they were not connected to each other, then it will do the union and return a false. So in the union function, first of all, what I'll be passing is I'll be passing I, j. Okay, then I'll be passing the parent array as well, I'll be passing the rank as well. All right, so these are the some of the parameters that I'll be passing. Apart from this, I think I can also pass the v value. So if it returns me a true, right, if I is lesser than j and the union function returns me a true, basically if the union function returns me a true, so that means that there is a cycle existing. So we could have also written is connected, or is connected kind of function to return if I and j are connected to each other or not. Okay, but I'm doing it in union. So if it is connected, right, so in that case I'll return a 1 or I can say that I'll return a true, indicating that okay, they both are connected to each other. Otherwise what will happen if it returns me a false? So before returning false, it will do the union part. And once this part is been done, So in that case, simply it will return a 0 from here, right? If suppose that in the end I never find a cycle after connecting, so I'll return a 0. And why I have taken this condition I is lesser than j? Because if 1 and 2 are like, if in the adjacency list of 1 2 is present, and in the adjacency list of 2 1 is present, so when I check for adjacency list of 2 where 1 will be present, then I can say that maybe cycle is present, because they have the same parent, because 2 will be having the parent 1, and 1 will be having the parent 1 as well. But actually that will not be true, so this case I need to understand. So that's why I'm returning a 1 from here, right? Now I will do what? I will write the union function. So let's say I'll write the bool union function here, in which first of all I'll be passing the a value, then I'll be passing the b value. After this I'll be passing the parent array as well, as I've passed in the main function. Then I'll pass the rank as well, because I'll be doing besides the like path compression, I'll be also doing the union by rank. Okay, so after this I'll also pass the n number of nodes that were there, that is nothing but n. Okay, although I know don't require it, I think, but still I'll pass it. So let's say a is equal to what? For a I'll find the ultimate parent, so a is equal to find parent of a, like okay, and b is equal to finding the parent for b as well, right? And I'll pass the parent array for that. And if it happens, right, if it happens that a is equal to b, in that case, if they both have the same parent, if they belong to the same component, in that case I'll return true. This will indicate that they have a cycle. If I is lesser than j and a is equal to b, in that case it will return me a true. That means that basically there is a cycle existing. Otherwise, if there is no cycle existing, as I said, in this case, when 2 is lesser than 3 and 2 and 3 are already belonging to the same component of 1, in that case if I connect 2 and 3, so I'll get a cycle, right? So in that case I'll return a true, that okay, there exists a cycle. Otherwise what I will do is, if there does not exist a cycle, so I'll check that, as I mentioned, I'll do the compression, I'll do the union by rank as well. So if the rank of I'll connect the smaller component into the bigger one. So if suppose that the rank of b, okay, if the rank of a is greater than the rank of b, in that case I will say that okay, the parent for b is equal to nothing but a. Okay, else if it happens, suppose that the rank of b is suppose that the rank of b is greater than the rank of a, it is greater than the rank of a, in that case what I'll do is I'll say that okay, parent of a is equal to nothing but b. And in the else part, when they both the components have the same size, then suppose that I merge it in a, so I'll say that rank of a plus plus, and apart from this I'll say that okay, the parent of b is equal to a. So this is how I will do the relationship thing. And then if after merging, so since they were not the same part of the same component initially, so I'll return a false, indicating that they were not part of the same component. Now I have written the code. Let's try and compile it to see if there is any error in this code. Okay, so I think we are getting the same output on as mentioned in the sample. Let's try and submit it. So you can see that our solution was able to pass all the test cases. In case if you understood this explanation for this finding the cycle using DSU, make sure to hit the like button and comment down understood as well. Thank you.